Hi guys, this is Rahul from Finance Excel. Today we will be learning, I will be explaining each and every component of the ANOVA table and the regression statistics that is generated by our Excel package. Right now, this is a continuation to the SBI versus Bank Nifty linear regression. Right, so we are basically analyzing the regression statistics and ANOVA of SBI versus Bank Nifty. Okay, so we start with analyzing each and every component, guys. See, multiple R would be applicable for multiple regression, so we are ignoring it for the time being. R square, what is R square? So let us start. Let me name this as 1, right? So 1 is R square or coefficient of determination, right? For simple linear regression, right? There are two ways to calculate R square. First way is R square is equal to SSR by SST, right? Second is, right, to square the correlation, right? We square the correlation between X and Y, right? Both would give us the same result. Both these two methods would give us the same result. Okay, interpretation of R square. Now guys, the R square here is 86.72% or 0.86718. So let us take it to be 86.72%. So interpretation of R square is that 86.72% of the total variation in the dependent variable is explained by the independent variable, right? So this is the interpretation of R square, right? Adjusted R square not applicable for simple linear regression, right? Then we move on to standard error. So let me name this as 2. Standard error is nothing but the standard error of the estimate, which is nothing but the standard deviation of residuals or standard deviation of the error terms, right? It is calculated as how root of MSE, where MSE is where MSE equals mean squared errors, right? I'll come as to how to calculate MSE and stuff, right? Okay. Now we come to the ANOVA table. ANOVA stands for analysis of variance, right? Okay. If you had gone through my previous video on linear regression, right, I had told you that SSR was 6797.41. This SSR was 6797.41. But before that, guys, what is the purpose of ANOVA? Right? See, the purpose of So I'm writing this down here. The purpose of ANOVA is to bifurcate the total variation in dependent variable into explained variation and unexplained variation, right? So total variation of 7838.46, right, is bifurcated into explained variation, which is SSR, and unexplained variation, which is SSE, right? So this is the purpose of ANOVA, to bifurcate the total variation in the dependent variable into explained variation and unexplained variation. So guys, SSR is 6797.41, right? How do we calculate SSR? SSR is y hat or y predicted minus y bar whole square, right? And higher the SSR, right, better the model, right? Because a higher SSR indicates that the majority of the total variation in the dependent variable is explained by the independent variable. Okay, now guys, we come to SSE. SSE. Okay, so SSE. Okay, SSR stands for sum of squared regression. Right now, SSE, right, is sum of squared errors, right, sum of squared errors, and it is calculated as y actual minus y predicted whole square, right? This is my SSE. It is the unexplained variation. SSR is the SSR is explained variation. SSE is unexplained variation, right? Unexplained variation. So lower the SSE, better the model, right? And basically, what is SSE? SSE is the variation in the dependent variable that is not explained by the independent variable or the regression model. This is what SSE is, right? Okay. A higher SSE implies that the majority of the variation in the dependent variable is not explained by regression model or the independent variable, right? Or you can say that the majority of the variation is explained by the error terms. Okay guys, now one more important point, you can see degree of freedom is 1. Degree of freedom is nothing but the number of independent variables. Now what does this mean? One independent variable is explaining 6797.41 out of the total variation of 7838, right? So out of the total variation of 7838, 6797.41 variation is explained by one independent variable, right? Okay, so now we are done with SSE, we are done with SSR, we come to SST. SST stands for sum of squared total. Guys, we are also done with DF of SSR, right? What we meant was that out of the total variation of 7838.46, right? 6797.41 is explained by one independent variable, right? Right. Then we have sum of squared total or SST. This is the total variation, right? And this is the total variation calculated as y minus y bar whole square, right? Is y minus y bar. So guys, just let me charge my laptop for a second. Okay. Just a second. Just a second. Okay. Okay guys, so here next is okay total DF. Total DF. Guys, always remember total DF would be n minus 1, right? In our case, we have 40 observations. So 40 minus 1 equal to 39, right? Guys, when we divide SST by total DF, we have SST is what? Y minus y bar whole square. Total DF is n minus 1. Now guys, this is nothing but variance of the dependent variable. Please remember this. It is the variance of the dependent variable, right? this formula, right? This formula is the same as the, this is the same as the, right, as the sample variance, right, which we had studied in descriptive statistics. So let us do this, guys. What is my y minus, what is my total variation? 7838.46 divided by 39. This will give me 200.986. Okay, so let us go to my Excel sheet once, guys. Yep. So my Excel is here. Okay. Second. Okay, guys. Now I'm back to my Excel. This is my linear regression sheet. Guys, if I take the variance of the dependent variable, please look, if I take the variance, sample variance of the dependent variable, it should come to 200.986. Please see, it is the 200.986, right? And it is nothing but SST by n minus 1, right? So we are good with this also. We are good with this. Okay. Degrees of freedom of residual is 38, right? Which is df of SSE is n minus 2, right? Guys, we had already discussed that the minimum number of observations to run a regression are 3, right? Guys, when n equals 2, then my r square will always equal 1, SSE would equal 0, and SSR would be SST, right? That is, we will not be able to assess the relationship between x and y. Guys, in fact, when there are two observations, there is no possibility of running a regression, right? So when there are two observations, no matter what the observations are, actual y will equal predicted y. This is very important. No matter what the observations are, actual I will equal predicted y. I will show this to you in a second, right? Okay, I'll come to this point after completing everything. I will come to this point, right? It is only when the third observation comes into picture right? The line of best fit or our regression models, right, has freedom to vary from the data points. So guys, when we have two observations, remember it does not matter what the two observations are, right? The line of best fit will intersect both these 2 points, right? It's only when the third observation comes into picture, the line of best fit or our regression model has freedom to vary from the data points, right? So I'll show this to you. So the point being is that when we have two observations, the line of best fit will intersect both these two observations. But when we have three observations, right, the line of best fit gains freedom to vary from the data points. So I'll explain this in some time. Okay, so this portion is done. I'll just explain this part in some time. Right now we have MSR, which is MSR is SSR by DF, which is what is our SSR here? 6797.41 by 1, right? So you can think of MSR is the as the average variation explained by each independent variable. So this is very important because under simple linear regression, guys, under simple linear regression, MSR equal to SSR because there is only one independent variable. Okay. Now we have MSE, right, guys? MSR full form is mean squared of regression. Now we have MSE, which is SSE by DF, or SSE by DF is n minus 2. SSE is what? Y actual minus Y predicted whole square. So in our case, SSE was 1041.05. N is 40. 40 minus 2, 38, which is 27.3961. 27.3961. Okay, guys, please remember MSE is nothing but the variance of the error terms, right? It is the variance of the error terms, right? So if I take a square root of MSE, what I get is the standard deviation of the error term. And at the starting of the discussion, I told you that the standard deviation of the error terms is nothing but SEE, or SEE is also known as standard error of the estimate or standard deviation of the error terms. Right. Now, since we are done with this, right, we are done with this, we are done with this, right? Now we come to the F statistic. F statistic is nothing but MSR by MSC, right? Yes, please remember, if MSR is a large number compared to MSC, this would imply that our model has great explanatory power, because numerator is MSR, which is equal to SSR, right? SSR is equal to MSR for simple linear regression, and if numerator is SSR, right, and SSR is a very large number compared to MSC, this would mean that the majority of the variation in the dependent variable is explained by the independent variable. So guys, if MSR is a large number compared to MSC, it would imply that our model has great explanatory power, because numerator is MSR, which is equal to SSR, and SSR is nothing but, then SSR means that if we have a high SSR, it means that the majority of the variation in the dependent variable is explained by the independent variable. So if we have a high SSR, this means that the majority of the variation in the dependent variable is explained by the independent variable. Now guys, if MSR is a large number to compared to MSC, my F statistic would be a large number. So this would mean that a large F statistic, right, implies a greater explanatory power of the model, right, and vice versa, right guys? So we are clear with ANOVA. We are good with coefficient. We are good with coefficient of intercept and coefficient of the slope, right? We are good with these two. Standard error is out of purview. Calculating the standard error is out of purview of L1 syllabus. So I am ignoring that for the time being, right? Okay. So basically now we have the T-stat. Under T-stat, we basically check whether the true slope coefficient and the true intercept is different from zero, right? So how do we calculate this? See, we are basically testing whether our true slope coefficient beta 1 is different from 0. So basically under this hypothesis test, my null is that beta 1 equals 0, and my alternate is beta 1 not equal to 0. Right, so we are basically standardizing the test statistic. We are basically standardizing the estimated slope coefficient. How do we standardize the estimated slope coefficient? Standardized slope coefficient is what? Beta 1 hat minus hypothesized value by standard error of the regression coefficient. Right, my beta 1 is how much here? Beta 1 hat is 0.013916. Just let it go down. Okay, there is some problem with the OneNote. I'll have to restart that. Just a second. I'll have to restart the OneNote, guys. Just a second. Okay, so I have started the OneNote. Okay, so my beta is 0.0139 minus 0.013916803 minus 0, which is my hypothesized value, divided by the standard error of the forecast, which is 0.000883511. 0.000883511. This would give me the T stat of 15.75. Right. Similarly, we can calculate the intercept. Right. Similarly, we can calculate the intercept of the slope coefficient. We can calculate the um, estimate of the intercept. Right. Similarly, we can calculate the estimate of the intercept. So this was our discussion on ANOVA, right? Guys, in the next video I will upload why do we have n minus 2 degrees of freedom, right? I will explain that logic in the next video. हाँ क्या हुआ पापा? नहीं नहीं अपने को नहीं पता, अपने को क्या पता.